Okay, so let's proceed with our lecture here on designing for low power. So this should be our last topic in the semester. Okay, so let's get to it. Why power matters? Why it matters? Number one is the packaging cost. So high power requires normally high cost in packaging. Power supply rail design, chip and system cooling cost, noise humidity and system reliability. So of course, when the system gets too hot, the operation of the transistors might change or alter slightly and impact the immunity and the reliability. Battery life as well. Okay, power will impact the battery life in portable systems, and also environmental concerns. Okay, some environmental concerns when it comes to power. So why do we worry about power? Let's see the power density year by year. So as we go on to 2010 and now we're in 2020, this is the projection. In fact, I think we've seen in the beginning the projection that the power is expected to increase exponentially, right? So expected to increase exponentially, but in fact it doesn't really go this way as we saturate or clamp down our operating frequency, and we manage to handle the power issue quite well nowadays. Okay, rocket nozzle. Chips might become hot or too hot. It is in fact true nowadays that our phone, our PC gets sometimes it can get a little quite hot. Okay, quite hot. So that's mainly the issue with power in the MOS transistors. What about standby power? So here we are looking at the year by year for VDD and the threshold voltage. So these two of the most important parameters when it comes to power and also speed. Okay, and also speed. It is really about how we control the values of VDD and the threshold voltage. So in 2002, the VDD 1.5. So you can say probably it's a 150 nanometer process, and then here in 2014 it might be probably around 60 nanometer. Okay, so 60 nanometer process, we have a 0.6 volt and the threshold voltage of 0.25. So as you can see, the threshold voltage keep decreasing and the VDD keep decreasing. Okay, drain leakage will increase as threshold voltage decrease to maintain noise margins and meet frequency demands, leading to excessive battery draining, standby power consumption. So the issue with reducing the threshold voltage is mainly drain leakage. Okay, because your threshold is too small, which makes the circuit or the device fast, but also susceptible to leakage current. Okay. Okay, let's look at the power energy figures of merit. Power consumption in watts determines the battery in battery life in hours. Peak power determines the power ground wiring design, sets packaging limits, impacts the signal noise margin and reliability analysis. Energy efficiency measured in joules, amount of power consumed over time. Okay, so how efficient is your energy consumption? And it's given by this equation. E is PT dt. So energy is simply power delay product, and joules is watt second. Joules is in the unit of watt second. So here is watt second. So lower energy number means less power to perform a computation at the same frequency. Okay, so it's something interesting to remember. E equals to PT. So power versus energy. So let's look at the first one here. So power is the height of the curve. So if we measure the power against time, So how much power we consume at a certain moment in time. So for example, at this moment we are consuming low power, and at this moment we are consuming relatively higher power. So lower power designs could simply be slower. So to do this particular task, using approach 1 and approach 2. So approach 1 will finish faster. Okay, so finish here, finish 1, and here is finish 2. Okay, so but the amount of energy used is the same. Okay, so energy is in fact the area under the curve. So you can see the area here, okay, is in fact the same as the area down there. So you can say that the two approaches require the same amount of energy, just that the first one finished faster, but requires a high power. Okay, so here you can see this is your delta P, and here is your delta T. Okay, so your energy is in fact delta P times the delta T. Okay, so power in the circuit element. So if we have a voltage source, so P VDD T equals to I DD T VDD. Okay, so in the voltage source, power across a resistor is I squared. I squared R is a power, so PRT, so I squared R here is your power. Okay, ID VDD is your power. Okay, so you can say it's your power, and then if you multiply with T, you get your energy. And your energy across a capacitor can be given by 1/2 CVC squared. Okay, which can be derived from here. So in the end, we have this quite important equation. The energy stored across a capacitor is given by 1/2 CVC squared. So C is the value or the size of the capacitor, and V is the voltage across the capacitor. You can also get the current across the capacitor, C dVc over dt. So charging a capacitor, because in our course is about charging the node, where the node consists of capacitors, load capacitor. So when charging a capacitor, when gate output rise, the energy stored in the capacitor is given by this one, as we derived in the previous slide, 1/2 CL VDD squared. Okay, so here's your CL, so 1/2 CL VDD squared is the energy stored in the capacitor. The energy drawn from supply is E VDD is equals to CL VDD squared. Okay, E VDD equals to CL VDD squared. Okay, so half of energy from VDD is dissipated in PMOS transistor as heat. The other half stored in the capacitor. Okay. Yeah. So basically the energy drawn here, E VDD is energy drawn up here is CL VDD squared, but half. So half is dissipated here. Okay, so we have E dissipated is 1/2 CL VDD squared, and then we have EC 1/2 CL VDD squared. Okay, so you have half dissipated in the PMOS, okay, and the other half is actually being stored in the capacitor. Okay, so when gate output falls, which is going from high to low, energy in capacitor is dumped to ground. Okay, so whatever energy that is stored here is going to be dumped all the way to ground, and then dissipated as heat in the NMOS transistor. Okay, so one thing to think is the reason why our device can get hot is because of the heat that is dissipated. in the transistors. Okay, so if you have like 1 billion transistor in the microprocessor, the Intel processor, 1 billion, and then you have heat dissipating from each of the transistors, and that's why your device gets hot. And the higher your energy that is dissipated, higher CL, VDD, then the higher the heat that's been dissipated. So power delay product, and the energy delay product is given by the equation PAV times TP equals to CL VDD squared. Okay, so this is basically your energy. Its power delay is basically your energy. So PDP is the average energy consumed per switching event. Okay, so per switching event, lower power design could simply be a slower design. The energy delay product is PT squared. Okay, PT squared. So is PDP times the TP. So EDP is the average energy consumed multiplied by the computation time required. Takes into account that one can trade increased delay for lower energy or operation via supply voltage scaling the increased delay but decreased energy consumption. Okay, so as you can see in this graph, we're looking at VDD from 0.5 to 2.5, and we're looking here at the energy delay product, the normalized energy delay product. So we're looking at this guy, and we can see that there's a trade-off between energy and delay, where if you want to minimize delay, then you are going to consume a high energy. Okay, and then which is typically the case. So if you want to have a fast circuit, you're going to use high power and high energy, as compared to if you want a small delay. Okay, small delay, then you can trade off with maybe lower energy. Okay, lower energy. Right? Okay, but then you can have an energy delay analysis, which is out there. Okay, so let's look at this important equation here, the CMOS energy and power equation. So we have the E here. So here is actually a dynamic. Okay, so here is your dynamic power. Okay, and then and here is your static. Okay, static power. So power in general can be divided into two parts. You have dynamic power and static power. So what is dynamic power? I think it's going to be explained in the next slide. So dynamic power is the power that is consumed when the chip or the transistor is in operation, when it's switching. And static power is the power that is consumed when it is not switching. Okay, and the component here. So here is the final one. So the component for the first part here is CL VDD squared F 0 to 1. Okay. Plus T short circuit time, the time duration that both the NMOS PMOS on, VDD, the peak current, times the F0 to 1. So this F0 to 1 is a very important parameter, which is simply F is the operating frequency, and P here is your switching activity factor. Okay, so basically for the first part here, you can say that is CL. So CL is your load capacitance. We've seen this many times. VDD is your supply, and your F01 consists of two parts, which is the switching activity factor. So how many the probability that that is switching from 0 to 1, okay, for that particular gate, and then the operating frequency. Okay, how frequent that the values can change. Okay, from 0 to 1. Let's look at the detail here. So this is also called the switching power, the short circuit power, and then we have the leakage power. Okay, so the total power. So here you can say the total power in the MOS circuit is actually the switching power, which happens during the switching of 0 to 1, short circuit is happen during both NMOS PMOS are on, and the leakage power is happen when the device is not in operation. Okay, so then we have the dynamic plus static, and the dynamic power is switching plus short circuit. And the static power consists of several components multiplied with VDD. So let's look at the dynamic power first. So in dynamic power, we have the switching power. So remember, it's CL VDD squared P01F. Okay, given something like this. Okay, so 1, 2, 3, 4. We have 4 components. Okay, we have 4 components in the switching, and then in the short circuit we have the short current, the short circuit, the time duration, I peak VDD. Okay, also P01F. Okay, so in the short circuit we also have that. Okay, these 2 components, we're going to look into more detail, in particular this one. So this one we are not going to be discussing in detail. It's quite tricky to calculate. I think we already did some analysis on the short circuit current. Okay, on the short circuit current and the short circuit power analysis in the previous slides. I think we've done a little bit on this. And the static power consists of the sub-threshold. Okay, so we have the sub-threshold, means we have a current flow at VGS less than VT. Okay, we have a current flow at the sub-threshold. We have the gate leakage. Okay, so there's a current going through the gate, even though it's supposed to be high resistance on the gate. Junction leakage, so we have a current going through your drain and the source, and going out to the substrate, and then we have the contention current on the output. Okay, so so one thing to note here is something interesting to consider is actually your P short circuit. Your P short circuit can be estimated as 10% of the P switching. So this is this is mentioned in one of the books. But if you don't want to calculate your short circuit power, then you can just estimate. You just find your switching power, and roughly you can say that your short circuit power is around 10% of your switching power. Okay, something interesting to consider. Okay, so the switching power consumption. Okay, so the dynamic power is CL VDD squared P021F. So remember these 4 components, very important components to remember. Okay, so it depends on your CL, depends on the VDD, depends on the probability of the output to switch from 0 to 1, and also the operating frequency. So if you have a register, okay, so if you have a reg, and there'll be a reg here, and you have a clock, okay, then you can have a F. Okay, so you can have a F here. So so you can imagine that you have a register, and if you have registers, then you have a clock with the operating frequency, and that operating frequency will determine how fast your gate will be switching. So that's your F there. Okay, and your P0 to 1 is there. So the probability that the output will switch from 0 to 1. It's not a function of transistor size, data dependent, a function of switching activity. So it's mainly a function of switching activity. And switching activity is given by these 2 terms there. How frequent is your gate going to switch? Okay, from 0 to 1, 1 to 0, that's the part where it's going to consume power. So if you can minimize or reduce the number of switching time, the frequency of the switching, then we might be able to reduce the dynamic power and reduce the heat as well. Okay, besides the VDD squared and CL, those two are important. VDD is particularly important, it's a squared term there. So if you can reduce your VDD, you will be able to reduce your dynamic power quite significantly. Okay, so lowering the switching power, P dynamic is CL V squared P021F. Okay, so go back here. So the capacitance, a function of fan out, wire length, transistor size. So if you can reduce any of these, you can reduce the dynamic power. Supply voltage has been dropping with successive generations of fab technology. Activity factor, how often on average do your wire switch? Clock frequency, is it increasing or decreasing? So as I mentioned, the clock frequency is quite stable now, saturate to around maximum 3 gigahertz, 2.8. Not getting any higher, so that we can control the dynamic. VDD is still dropping, but not so much. We cannot go too low on the VDD. So CL is quite constant, cannot change that, and the switching frequency also depends on F. So the short circuit power consumption, so let's see what's going on here. So the short circuit happens when both on. Okay, and remember, both on happens there. Okay, when your input is VM, and both can be in saturation or maybe velocity saturation even. So when both are on, then you're going to have a current flow from VDD all the way to ground. Okay, the finite slope of the input signal causes a direct current path between VDD and ground for a short period of time during switching when both the NMOS PMOS transistors are conducting. Short circuit current determinates. So the energy of the short circuit is I VDD TSC, and then the power is I VDD TSC F01. Okay, where F0 is P01 times F. Duration of the input signal TSC depends on the slope. I peak is determined by the saturation current of the P and N transistors, which depend on the size, process energy, and temperature. The strong functional ratio between the input and output slopes is a function of CL. So I'm not going to go through in too much detail. As I mentioned, we can estimate like 10% of the dynamic, the switching power for your short circuit. The impact of CL on the short circuit. So the short circuit current also depends on CL. Okay, so we can see here that if your CL is small, if your CL is large, then you have quite a small slope, and here is a sharp slope. Okay, so small CL we get a sharp slope. Okay, and what happens if you have a sharp slope? Then your TSC is small. Okay, TSC is small, here is TSC big. Okay, and remember your power on the short circuit depends on your time duration of both devices to be on. So you want to have a minimum duration where both devices are on. Okay. Okay. Switching power reduction. So we know the terms. So how to minimize power, and that's a key issue nowadays. As people go using mobile and portable devices, so people talk about sometimes power is more important than delay. So as designer, I think we need to know exactly, what are the factors that impact the power and how to design so that we can obtain low power. So here is clear that if you can reduce the activity factor, reduce the capacitance on the output node, reduce the supply voltage VDD, reduce the frequency, we should be able to reduce the dynamic power consumption. So some of the methods, clock gating, the best way to reduce activity is to turn off the clock to registers in unused blocks. So basically here we put a clock gator. So if you put a 0 on the clock, okay, so based on the enable logic, so if you put a 0 on the clock, then you will have no activity. Okay, here is your combinational logic. So if you put a 0, you're going to have no activity on the clock. Gate capacitance. Can we make few stages of logic? Can we make small gate size? If you're able to make this, you can reduce the power. Wire capacitors, good floor planning, keep communicating blocks close to each other. Don't make the wire too long. Okay, the length of the wire will impact your CL. Okay, so make sure your wire is not too long if possible. Drive long wires with inverters or buffers rather than complex gates. Okay, we've seen the logical effort method for this. Voltage frequency, run each block at the lowest possible voltage frequency that meets the performance requirements. Voltage domain, dynamic voltage scaling. So this is a quite relevant method today, where we usually have multiple domains of voltage and frequency. So some part of the chip runs at different VDD than the other part. So if you're able to do this, you provide separate supplies to differential blocks, level converters required when crossing from low to high VDD domains. So there's a challenge to it when designing with different domains, voltage frequency domain. And the dynamic voltage scaling is also important and quite a widely used concept today, sometimes called DBFS, okay, frequency. So we have dynamic voltage and frequency scaling. So the voltage and frequency is scaled dynamically, okay, while the chip is running. So adjust VDD and F according to the workload. So for example, if the workload is big, then you want to be fast, you increase your VDD, but if your workload is small, then it dynamically reduces your VDD and your frequency so that your power will be reduced. Okay, your power will reduce dynamically. So you have some logic here. So it is quite practical and quite widely used today as far as I know. Okay, so I think that's this part of the video. So in the next part of the video, we'll talk about the static power and some analysis on dynamic.